everyone, my name is Natalia and I'm a software engineer manager at Google. I work on hiring products and also help out with coding competitions. We hope you enjoyed all of the problems from our 2021 contest. Today, Pablo and I are going to talk you through the problem Infinitree from the 2021 CodeJam finals. Pablo, do you want to introduce yourself?
Hello Natalia, hello everyone. My name is Pablo. I'm a software engineer and work full-time on coding competitions. We will talk about what Infinitree asks us to do, and later discuss the solution a little bit. Remember, you can always try any of our problems on your own at any time in practice mode on g.co/codejam. Now, let's get started.
As you may have guessed, in Infinitree, we will be working with a possibly infinite tree. The tree is strictly binary, that is, every node has either two direct children or none.
Natalia, the input to the problem will still be finite, right?
Yes, Pablo, that's a good point. The tree is defined recursively from the root based on colors. There is a finite number of colors. A white node has no children. A node with a non-white color C has exactly two children, a left child of color LC and a right child of color RC. These L and R values are the input. The root has a fixed color, black.
Okay, so we generate the tree by starting with the black node at the root. Then we attach two nodes with colors L black and R black to it. Then we attach LL black and RL black to the left node, and so on.
Yes, as long as a node is non-white, it should eventually get its children attached to it by the process.
I see, Natalia. So this process may never end and keep producing an infinite tree, like the one on the left, but it can also end and produce a finite tree, like the example on the right.
Indeed. Then we give numbers to the nodes of the tree from top to bottom and left to right.
So the root always has number 1, but other nodes have a number that does not depend solely on their color, as we now see in the example trees.
Exactly. We are now given two node numbers A and B. We need to find the distance in the tree between them.
Distance between nodes in a tree? That sounds like an old and well-studied problem to me.
Pablo, that is certainly true. But we have a case here where the node numbers can be really large, up to 10 to the 18th.
Okay, so no building even just the relevant part of the tree in memory then. Natalia, those huge numbers sound really hard to deal with.
They are CodeJam finals hard, and maybe even more.
So, to solve the problem, we may need to work symbolically to avoid those huge structures that won't fit in memory.
The input already represents the infinite tree in a condensed way. Maybe we can do the same with the other objects we need.
That's a great idea, Natalia. Remembering the way we built the tree before, we can represent branches as paths on the directed graph implied by the L and R edges between colors.
The nodes at a particular level of the tree would be the ends of paths of a particular length.
Right, and paths of a length k in a directed graph can be counted by powering the adjacency matrix of the graph to its kth power. And powering matrices can be done efficiently.
It sounds like we could find out the level of the given nodes using bisection. We just need to be able to count the number of nodes up to a certain level, not just exactly at one.
Natalia, I learned in school that you can efficiently compute the summation of all powers of a matrix with the divide and conquer technique.
Okay, Pablo, that helps us calculate for any given level how many nodes the tree has up to that level. Using the bisection method, sometimes known as binary search, we can get the first point at which that function is greater than the node numbers A or B and know their level.
In test set 1 of the problem, node A is always the root, which means the level of B is equal to the distance between them. With the work we have done, we at least got some points out of this problem.
We must be on the right track, Pablo. Let's keep going. If we know how to calculate the level of any node, we can express the distance between A and B as the sum of their levels minus the level of their least common ancestor. If we can compute that least common ancestor, then we're done.
Yet another well-studied problem, but in a gigantic tree.
Yeah, speaking about typical work on trees, the way you usually work on them is by going into subtrees. However, the node numbering is a problem because the node's number is affected by all nodes, so it is hard to adjust it when moving to a subtree.
We could try to use a better naming system for nodes. For example, we could use a pair of numbers consisting of the level, that we already know how to calculate, and the offset, that is, the number of nodes to the left at the same level, like a coordinate system. We already know how to calculate levels given a node number. and we can calculate the initial offset as the difference between the node number and the number of nodes up to the previous level.
Okay, Pablo. So a node at level k and with x nodes on its left would be the node at level k minus 1 with the same offset in the left subtree. But what about moving to the right subtree?
We will have to subtract from x the number of nodes at the same level that were left behind.
Counting that offset difference sounds similar to what we've already done. It is exactly the number of paths of length k that start at the root color. We can also use the kth power of the adjacency matrix for that.
I see. So, if the number of nodes in the left subtree at level k-1 is at least x, that means the node represented by kx is on the left subtree. If not, it is on the right.
You can turn that into an algorithm by simply moving down from the root as long as both input nodes are on the same subtree. Once they're not, the current root is their lowest common ancestor, so the sum of their levels is the answer.
Nice observation, Natalia. That can help us solve more cases than before, but only when the lowest common ancestor is not too far from the root. Otherwise, this will take a long time.
That's true, Pablo. On many trees, the level of a node is just logarithmic on its node number and the solution will work. Maybe we can move multiple steps at once in the other cases.
For the number of nodes not to grow exponentially, each color from the input graph must be in at most one cycle. We should be able to process multiple passes through those cycles efficiently, generalizing what we did to process a single step.
I think you're right, Pablo. But we don't have time for all the details here. A detailed description of the entire solution is available in the Analysis tab of the problem page. It is already available at g.co/codejam.
Stopping sounds like a right call. Thanks for watching, everyone. We hope you enjoyed it. Remember to check out our videos from the other finance problems.
Bye, Pablo. Bye, everyone.
Goodbye.